Our next presentation comes from Nils Meinhard. Nils comes from the University of Technology in Darmstadt in Germany, and he's talking about the internal stress across the automotive windshield. So we all have seen that, at least here in Finland, time to time in winter, we get the spikes from the car in front of us hit our windscreen, and then we got some lines. So Nils, please go ahead.
Okay. Yeah, thank you very much for the introduction. Today I will talk about the distribution of internal stresses across automotive windshields. I will talk about my motivation, have a little bit about the test setup, then the actual internal stresses, and I will conclude with an outlook. So first about the motivation. Our principal goal is to develop a method for the numerical simulation of the post-fracture behavior of the laminated safety glass. Just to remind you, laminated safety glass is a composite of glass interlayer glass. So the glass is bonded to the interlayer, and because of that, we remain a load-bearing capacity even after fracture. There are many use cases for this. In our use case we are investigating here, we are doing the head impact on the windshield, so we're in the automotive sector, and down here you can see such a head impact test. So this is the head impactor, which is shot directly on the windscreen where the windscreen breaks. This load case we've seen here is the Euro NCAP test, and from that test we get that HIC value, and this is the head injury criterion. This means the higher this value is, the higher is the risk in getting injured for the pedestrian safety or for the inmate safety. And this is a function of the acceleration, and this is the acceleration of this head impactor. Down here you can find an acceleration curve of this head impactor, and you can see here that you can divide this into two parts. So the first part, this side here the windscreen isn't broken, so here you have an only elastic state. At somewhere around this point here, the windscreen breaks, and everything that is after that is the post-breakage behavior. And when you see this comparison between the experiment and the simulation, you can see at the moment we pretty much can predict the pre-breakage behavior pretty well. So we can do the elastic state of the windscreen pretty well, and we can predict when the windscreen breaks. But everything after that, the post-breakage behavior, at the moment we can't really good describe. And for this HIC value, we actually need the whole process, because you have to vary these time T1 and T2 so that this value is maximized. And yeah, for this we need the whole experiment, not only the elastic state. Okay, what is the problem? What is the root cause for the disparities in the post-breakage behavior? The first problem is that we have problems in discretizing the crack width. So we get large deviations between the crack width in the experiment and the simulation. And the problem is when you have very small cracks, a small mistake in predicting this crack width will cause some huge differences in your results. So this is one big problem. And the other big problem is right now that we don't consider stiffness changes depending on the degree of fragmentation. So right now what we're doing is we are doing a 0 or 1 kind of statement. So either we have the full stiffness of the laminate, or we only have the PVB interlayer. This is clearly not the case in reality, so we see different zones of fragmentation. For example, here in the middle we have a pretty high fragmentation rate with very small fragments, and so in some outer circles here we get a lower fragmentation rate with bigger fragments. And this we want to consider in our project. And how is our approach to actually describe this post-breakage behavior? So we have an experimental part and the simulation part. In the experiment part, the first thing we will do is do the actual head impact test. Having this as a basis, we will go to the simulation, and the first big part here will be to predict the actual fragmentation rate. So we need to know where are cracks and how many there are. So when we know that, we will do further experiments. We need to characterize this residual stiffness of the broken laminate. We will do this with small sample tests, and there we will vary the fragmentation and the strain rate. What we will do here is not describe the actual, like, very precise behavior of this laminate. So we will investigate how one fragment behaves to another one and to the laminate and the delamination. But what we will do is produce a smeared material model, and this we will integrate into a numerical model by mapping the residual stiffness on the glass or the interlayer. This we will put on the prediction of the fragmentation rate and hopefully have the full picture, which we will then validate with these full head impact tests. The focus here is the prediction of the fragmentation rate, and the first thing you need to know here is that the fragmentation rate is highly governed by the energy at the moment of fracture. And this energy, this total energy, consists of two parts. So the first part is the elastic strain energy. This is caused directly from the head impact. And the other part are the internal stresses. So these come out of the production process and store some energy in the windshield. So here I will talk about the residual stresses in the glass. And here I will present my test setup. So the first problem with our windshields is that they are curved. So when you just lay them on the ground and do your stress measurements, you have high bending stresses. This means the goal is that we need bending stress-free support conditions. How do we achieve this? We need a support that exactly follows the shape of the windscreen, and there are probably a variety of ways to achieve this. I did a, let's say, practical approach here. I just sprayed some construction foam into the windshield, into the standing windshield. So I got something like an exact print of the windscreen. This is the back side of this construction. So the actual windscreen lays on the other side when we lay this on the ground. And that way, as I said, we get a print of the windscreen, and every single point of the windscreen is more or less supported. I put here a wooden frame on it just to increase a little bit the stiffness of this whole construction and to have the opportunity to lay it plainly on the ground. And at the end, just to even out some unevennesses out of the hardening process of this foam construction, I put a flat air cushion between these two. And that way, I got pretty much bending stress-free support conditions. I did my measurements with the scalp measurement device. I guess some of you will know this. This is a device that sends a laser into the glass and measures the backscattering retardation of the light. And from this, we can calculate the actual stresses and the stresses across the thickness of the glass, which is important for us later on. I measured in a 10 times 10 centimeters grid. I measured always in position 1 and position 4, so from the outside and the inside. But talking about some limitations, so the first limitation is the curvature. So when we have a very high curvature, especially in the edge areas, there were no measurements possible, or we didn't get really reliable results here. And the other problem is the black print, because as you can see here to the left, the black print is applied directly on the glass. So when we try to measure here, we don't get results. Okay, now to the actual internal stresses. Here I got you an example result for the surface stresses on position 1. So we have the first principal stress and the second principal stress and the corresponding directions. And the first observation we can make here is that we only have compression stresses across the whole surface. And these stresses range from -2 megapascals up to minus 16 megapascals. And what we can see is that they tend to increase from the middle to the edges. So here in the middle for the second principal stresses, we are around, let's say, I don't know, minus 10 megapascals, and up in the edge corner area, we get these minus 60 megapascals. In the middle, they tend to be a little bit more isotropic, and towards the edges, they are more aligned. But looking at these results, we have to acknowledge that the sculpt can be pretty inaccurate. So especially in regions where our stresses are under 4 megapascals, then we can get inaccuracies up to 25%, which is pretty much. This doesn't count for the whole windscreen, but we have areas where this is a problem. So we have to acknowledge that. And what we see here is more of a general stress level rather than talking about statements for discrete measurement points. So, yeah, but nevertheless, I think we can get a pretty good picture how these stresses are distributed across the surface of the windscreen. But as I said, we want the energy level that is stored in the windscreen. And this energy is obtained by integrating the stresses through the thickness of the glass. So we need to look at the distribution of the thickness. Here I got you two distributions, a blue line and a green line. And for both, this brighter blue line here indicates the measurement depth. So I measured into the glass from one side and stopped directly in front of the PVB. And for the blue line here, you can see this is a distribution that we would expect for, let's say, a tempered glass. So we have compression stresses at the surface and tension in the core, and this is pretty much parabolic and symmetrical to the center of the glass. So this is pretty much what we would expect and aligns pretty well to the literature. But we have, in some cases, distributions like the green line. Here we still have this general distribution, but here the symmetry axis doesn't match anymore. And we have two assumptions why that is. So the first assumption is that this comes out of the production process. So every edge and every corner, and especially every curvature, is basically a geometrical thermal bridge, and these result in uneven cooling processes and kind of this stuff. And from these distribution can result. The other topic is, as I said, we have inaccuracies. So in some areas here, we can expect that these come just out of the inaccuracies. Okay, but I think we can get a good picture about the distribution across the thickness. What do we have to do now? We have to combine these with the energy that is induced by the actual head impact, and then we get a prediction of the fragmentation rate. I will explain this picture in a second. First, I want to introduce the actual head impact to explain that. So this is the head impact we do in our laboratory. It's a little bit more simplified test here. So we have our windscreen only 4-point supported. And our head impactor here had a constant velocity. I have here a short video where you can see this. So head impact, glass fracture, and that's the whole experiment here. We can split this into 3 parts. So the initial state, nothing happened here. No head impact at this point. Then we have elastic deformation. So no cracks here, but elastic deformation. And we have the glass fracture where pretty much the experiment ends. And what was this picture I just showed you? This is the energy level directly at the end of the elastic deformation. So this is the elastic strain energy we get out of the head impact. So the head impact has some kinetic energy, and this translates into elastic strain during the head impact, and this is the energy we can get out of this. And this is exactly at the end of the elastic deformation, right at the moment of glass fracture. And with this, we know the energy we have in the windshield present, and we predict the fragmentation rate. But what we need to understand about this picture is that it does not really predict directly the fragmentation rate, but what it does is we know that when a crack grows through an area with high energy, then we will likely see there some high fragmentation rate. So we cannot automatically see, for example, here that we will have there a higher fragmentation rate than here. But when a crack goes there, then we know the fragmentation rate will be higher there. Okay, now we can compare these to the actual experiments for the inner and the outer glass layer. And especially for the inner glass layer, we can see here that this comparison fits rather well at this point. For the outer glass layer, this doesn't align that good as for the inner glass layer. In that case, we think that the inner glass layer actually broke first. So as I said, this is a simulation for the first glass fracture. And as we don't know which one of the first panes broke first, we expect that this here broke in a later moment of the experiment. So we have more energy there because it's later in the it's a later moment in the experiment. So that's an explanation why this fits. This one doesn't fit at the moment, and this left one, so the inner glass layer, fits. What do we need to do now? We need to implement the energy that is induced by the internal stresses. So right now it's only from the head impact, the elastic strain energy, and by implementing the energy from the internal stresses, we hopefully get the whole picture. Okay, for an outlook, the first thing, as I said, we need to finalize the prediction of the crack pattern. And something we want to do here is to actually analyze the crack pattern that we get out of the experiment. So I got you here two pictures. This is the same windscreen from a head impact test, and through some post-processing and some playing with lights, we could pretty much separate the pictures for the crack pattern of both panes. And when I just delete out the actual pictures behind it, we can see that these crack patterns differ significantly. And what we want to do here is to mathematically describe this picture and then define some zones of same characteristic, for example, the fragmentation rate. But when you look at these pictures, you have a variety of characteristica you could define here. So about fragmentation rate, about how these cracks align for the inner and the outer glass layer, and any kind of stuff. For all these characteristica we will see from these pictures, we will determine the residual stiffness of these characteristica, and we'll do some small sample tests. So we will have some small samples. We will put the damage on them as we see them here in the pictures, and then do some tests with varying strain rates here. From this, as I said in the motivation, we will derive a material model and implement this to a numerical model. So at this point, we hope we get the full picture. So we know where cracks are and how many. We have a material model for this, and that way we have the full simulation. And at the end, we will do a validation through the full sample tests. Here's some acknowledgements, and thank you for your attention.